Go full screen.
We should share first.
And
Window.
it's supposed to be like sweet and like very clean. And it's like
This will aid you through.
lychee, and then they poured olive juice all over it. It's just like this.
Okay.
It's funny thought. And I was like, I can't hear this. I have to leave this.
And then you lead us into lunch.
Correct.
No.
Yeah.
Yes.
That's right.
Okay.
That's right. Okay. Let's see. I thank the organizer for the invitation to speak. So I'm going to talk about 3 problems in additive number theory. I will start with an apology because I didn't quite realize that when you have 80 speakers in a meeting, and everyone generates a certain number of emails, which becomes large. So I didn't really have time to put this together the way I wanted, but I had given lectures on each of these 3 problems. So the simplest thing would be to concatenate them. Of course, then you have a 3-hour lecture. So you have to make some random deletions, which is what I did, and we'll see what is on here. I also, so these are like newish problems. That is, I think they're new. I'm not sure if they're new. It doesn't really matter. What I don't claim is that they're important problems. I have no idea what is an important problem. I am reminded of on Kissinger's first visit to China. You know, there had been no high-level official meetings between U.S. and People's Republic of China officials. And then Kissinger made his secret visit to China, and he met Zhou Enlai. And he asked Zhou, what do you think of the French Revolution? And Zhou was supposed to have replied, it's too soon to tell. So that's the way I look at problems in mathematics. You know, lots of people, including friends of mine, like to pontificate about what is important and what is not important. I have no idea. So there are 3 problems. Also, as you can tell by the organization of this meeting, I am probably the least computer competent person in the room. But somehow, even though these problems are very new, all within the last year and a half or so, somehow each of them has been attacked by other people using AI. It's somehow like symptomatic of how AI is very rapidly intruding, if you like, into mathematics. So the first problem is on sums of sets of finite sets of integers. Tim Gowers has a whole long blog post describing how he used Chat GP2 5.5 Pro to attack one of these problems. The second problem has to do with intersections of sum sets. And there's a company called Harmonic that has this computer software system called Aristotle to solve problems in mathematics, and built into Aristotle is lean. So it checks the correctness of every proof. Now, there is a question whether if lean says the proof is correct, you believe it. That is, it may be correct, but that doesn't mean you believe it, right? I mean, you know, you don't believe it unless you understand it. Oh, Jesus. Everyone's supposed to have their phones off. Yeah. And then on that same problem, the Chudnovskys used ChatGPT 5.5 Pro also to attack a different one of those problems. And on the last set of problems, negativity, whatever that is, they're problems that were approached by people at Harmonic, Pietro Mattaconi and Wouters van Doorn, who did something that Pomerantz Carl referred to in his talk. And they sort of brought me in, and it came up like this. This is actually all wasting my time, wasting your time. Harmonic had solved some Erdős problems. Aristotle had solved some Erdős problems. And evidently some people complained or said, well, Erdős is dead. It's like, you know, so his problems, you know, you need to find like a living research mathematician with problems and solve one of those problems. And then evidently someone told these people at Harmonic, there's this guy, Nathanson, who has a lot of problems. So they took my most recent paper on archive, which had a lot of problems, and they tried them all, and they solved one of them beautifully, I have to say, beautifully. And they posted it on archive, and they never told me. But you know, you have these things on your email that come up that says someone just cited one of your papers, right? And I usually ignore half of them, but I happened to click on that one, and I saw Aristotle had actually solved the problem. It was really very interesting to dissect what I had done and what was in my paper that Aristotle used, but what Aristotle used that was not in my paper that really was an original idea. And I was really impressed. And I told the guys at Harmonic, I emailed them, and I said, this is really pretty good. Whereupon they sent out press releases. Right? Because you have to ask, why are these companies spending a lot of money trying to prove theorems in mathematics? You know, they have billion-plus valuations. Why are they doing this? Well, I could explain why, I think. But anyway, okay. But this also raises the following question. So there's a former math major. So Max yesterday spoke about a very bright undergraduate who had done some work with him and then gone into finance. There was another very bright undergraduate math major who left the field, didn't go into finance, went into a different field where he was very successful, and that's Pope Leo XIV. And just about the time I was writing up one of these papers, he issued his first encyclical on AI, which is really a very impressive document. I really recommend it. It's long. It's not possible to provide a single comprehensive definition of AI. What can be stated, however, is that we must avoid the misconception of equating this type of intelligence with that of human beings. And so that's Leo. So artificial intelligence today, and I wrote this in May. I was posting this paper actually the same day that the encyclical came out, and I added this immediately because I like this. Anyway, these AI systems can solve mathematical problems sufficiently difficult to constitute an acceptable PhD thesis, and they have even solved a few significantly more important problems. But AI has not yet been able to decide what is an interesting problem, nor to formulate new conjectures in new areas of research. That is the perhaps transitory advantage that we humans retain. So perhaps the future job description of a mathematician will be decide what problems are easy enough for AI to solve, invent problems too hard for AI to solve problems too hard for AI to solve, discover new and interesting fields of mathematics, right? And describe the beauty in a piece of mathematics. Right? So in this talk, there's some questions in additive number theory. All should be solvable by humans, and some by the AI systems now being applied to questions in number theory. And I added this morning. My own experience with AI is extremely limited. But for $20 a month, I have Claude.ai. And I've asked it to solve some problems. And when I first wrote this, I said AI could not make conjectures. I gave it some problems. And my $20 a month Claude.ai generated some numbers. And then it basically said, but I conjecture that in general, these sets will have the following structure. Right? It didn't use the word conjecture. It looks like, right? But it really did it. I mean, it's mind-boggling to me. Okay. So let me start with these three problems. In their famous 1983 paper on sum product conjecture, Erdős and Semiretti wrote the following: if you take a number t between 2k minus 1 and k squared plus k over 2, it's easy to see that one can find a sequence of integers, that is a set of k integers, so that there should be exactly t distinct integers in the sequence ai plus aj, that is a twofold subset. So Kevin O'Brien sent me this and asked me if I could prove it, because it's just a sentence in the paper. And I wrote out a proof, but then it was actually interesting because, you know, in additive number theory, in this little piece of it, there's a huge amount of study of sets with very small sum sets. That's Grigori-Freiman's inverse theorems in additive number theory, which have generated have had huge impact. On the other hand, you have some sets with very large, whose cardinality is very large, like as large as possible. They're sit-on sets or things close to them, and they also have had a huge impact. But what about everything in between? I hadn't seen any study of like the range of possible sizes of h-fold sum sets of a set of k integers. So I sort of thought about that a little bit. And so what I'm interested in is this set RHK. So this is the set of all sum set sizes of h-fold sums of a set of k integers. All right? So that's a set of integers. And it's bounded below by 2k minus 1. That's when you have an arithmetic progression of length k. It's bounded above by k plus 1 choose 2, which is when you have a sit-on set. And the Erder-Semereti statement is that the set, this R of 2k, that is all possible sizes of two-fold sums of a set of k integers, those sizes form an interval, right? So it's true, right? It's true. But one can also ask the question, so given a number t in that interval, exists a set of that size constructed. And in general, is there an algorithm, some easy way to do that? And so the second part of what I had shown at the time was that, in fact, you only have to look at sets A in the interval from 0 to 2 to the k minus 1. And in that interval, if you look at k element subsets of sets in that interval, you will get the full range of subset sizes. So it's sort of like you can do that in exponential time, which evidently is like bad. So, okay. And so then you ask, because this is the business everyone, almost half the world is in, you know, is there a sub-exponential bound or a polynomial bound for this? So Tim Gowers, a few days, so Tim Gowers in May actually devoted one of his blogs to this subject. Because I had mentioned this in a previous, so he said, I decided to see how ChatGPT 5.5 Pro would fare with the selection of problems in a paper by Mel Nathanson entitled Diversity, Equity, and Inclusion for Problems in Number Theory and Additive Number Theory. So let me just digress 1 second. So this was the title of my paper. I gave it in a talk in the New York Number Theory Seminar. It was fine. I was going to the Devil's Den, the state of Florida, and I gave this in a talk at the University of Florida for Aladi's birthday thing. It was fine. I sent it for publication to the Notices of the American Math Society, and the acting editor, Joe Silverman, wrote back and he said, because what the paper was about, different problems in additive number theory, the diversity of them, and on the theme of it's hard to predict the importance of something, certain problems like Erder's sum product that were completely ignored for decades and then suddenly became important, right? So these questions of what is included in the canon and equity. So I sent it to Joe Silverman. He wrote back, basically, I loved your paper, especially like the fact that you have all these problems that were forgotten and then now we realize they're important. And we'll publish it, but there's only one condition. You have to delete every use of the word diversity, equity, or inclusion from your paper. And I said, politely, no, because if you look at if you look at a dictionary, there are various swear words in the dictionary. If you look it up, it has a definition, but it'll say in square brackets something like obscenity or something. But none of those three words, diversity, equity, or inclusion, is an obscenity. I mean, it's like you're allowed to use them in polite discourse. So, and for some reason, that's the paper that Tim Gowers actually read, and he found these problems. And he actually referred to the little theorem I just mentioned, where if we're looking at twofold sums, I had this exponential bound 2 to the k, right? If you look at k element subsets between 0 and 2 to the k, you'll get all possible sum set sizes. And Tim writes, ChatGPT 5.5 Pro thought for 17 minutes and 5 seconds before providing a construction that yielded a quadratic upper bound. A lot better than exponential if you're in the algorithms business, which is clearly best possible. And he describes that a bit more in the blog. But we're interested in this question of the range of sum set sizes. Even if you're just looking at twofold sums, in some sense, which you can make quantitative, almost all sets really are sit-on sets. I mean, if you take a set of k integers at random, there's what they now call additive energy is like 0, right? It's like A plus B is not equal to C plus D. So that takes care of most sets. So we're really interested in the other sizes of some sets. And sometimes they're there, but they're hard to find. And I wanted to look for some of them. And so in the case of twofold sums, you have an interval. So the first question is, if you look at h-fold sums for each of these three, is this always an interval of consecutive integers? So Noah Kravitz and I have written down somewhere that if you're looking at h-fold sums of k of a set of k integers, you will get all possible sum set sizes by only looking at the interval from 1 up to this basically h to the k minus 1. It doesn't say you get everything, but it says everything there is will exist in that interval. All right. Now, for twofold sums, we have the Herder-Semeradi statement. For threefold sums, these are the upper and lower bounds. So the simplest thing is to try k equal 3. So if you we're looking at sums, threefold sums of a set of 3 integers. So it's between 7 and 10, which, if you're a number theorist, means it's either 7, 8, 9, or 10. Now, you go to your computer, and again, at my campus, when we teach calculus, it's like with chemistry. You have the lecture and the lab. So in our calculus, there's the lecture and the lab. And the lab is Maple. So I know Maple. And I can program in Maple and not in anything else. And Maple can choose sets at random. So I had Maple choosing, hundreds, thousands, tens of thousands of random sets, looking at of size 3, looking at the threefold sums and seeing how big the sum set was. And you got 7, 9, and 10 very often. Like 0, 1, 2 added to itself 3 times has 7 elements. And for 9 and 10, they're the others, but there's no 8. So you ask, is there a set of 3 elements whose threefold sum has size 8? And the answer is no. No, right? So you ask, why not? Right? Now, this is not the same as proving that the answer is no. That is, once you know, in your head that the answer is no, you can sit down and give a proof. But that doesn't mean you can say why there isn't a set of 3 elements whose threefold sum is size 8. That is, because if you could understand that, you would understand a lot about why other numbers might not occur. Right? So the first little result was for h and k both at least 3, if you're looking at h-fold sum of a set of k elements, the smallest it can be is hk minus h plus 1. That's for an arithmetic progression. But the next larger number that is never there, which is like 7 is there, but 8 is not there. And so it raises the question, what are the other missing sum set sizes? So I have a student, Vincent Shanina, here at the Grad Center, who found a whole interval at the bottom that was missing, not just the smallest, but a little bit more. And yeah, so for sets of size 3, yeah, okay. Yeah, so for threefold sums for sets of size 3, 8 is missing, right? So you look at, instead of just threefold sums, higher sums. So remember this R of H3 means you look at H-fold sums of a set of size 3. So if you're looking at one-fold sums, it's just 3, right? I mean, if you're looking at two-fold sums, it's 5 or 6. If you're looking at threefold sums, it's 7, 9, or 10. If you look at fourfold sums, it's between 9 and 15. This is not what it is. This is what the numbers my computer is generating when I have it, just choosing sets at random and looking at the sum set sizes. And if you do more, you get more numbers. So, for example, if you look at 13-fold sums of sets of size 3, it's between 27 and 105. The smallest always occur for an arithmetic progression. The largest always occur for a sit-on set. And you get some other numbers. So you look at those numbers and you say, okay, that doesn't mean those are the only ones, but those are ones the computer has found. So you look for a pattern. Now, of course, now I know better. Now I would just ask chat. No, I don't have access to chat, except it's the not the serious one, the one that Tim Gowers uses and others. I would ask Claude, what are these numbers? It would probably tell me. I had to do it the hard way with a lot of paper. So these numbers are exactly the maximum minus the triangular numbers, right? Yeah, that's kind of interesting. And in fact, that's all they are. Those are the only ones that occur. If you're looking at H-fold sums of a set of 3 elements, this collection of numbers is the set of all possible sum set sizes. And for any given t, so there's a set of 3 numbers whose H-fold sum has cardinality exactly H plus 2 choose t minus the triangular number t choose 2. Here's a set 0, A, and B. So B is H plus 2 minus T. So if given T, that define B by H plus 2 minus B, A can be anything in the interval between 1 and B minus 1. And these sets all have size T. What about if you look at sets with 4 elements? We don't know what that is, actually. But if you look at it, so you have Maple. And again, I'm sure that half the world, has something better than my old MacBook Pro and better software than better programming language than Maple. But I started generating 4-element sets and looking at the H-fold sums and and you see certain numbers come up a lot and other numbers don't come up. And I couldn't actually make it into a slide. But for sets of size 4, for H equal 9, the bottom line, what were the sets that came up a lot? So the maximum is a sit-on set. That comes up 99% of the time. More than that, but whatever. But not 100%. And then you have these numbers. These are there are other numbers that come up, but these are the popular sizes. And somehow, with my primitive Maple ability, I managed to actually plot for size 4, sets of size 4, and 9, let's say 9-fold sum sets. How many, if let's say you pick 10,000 4-element sets at random, and you look at their sizes, but you count how many of each size occurs. And what you get is something like the spectra you would see when you were like studying physics or chemistry. Like, I mean, like there were really these peaks. And that was really interesting. Like, why should some numbers be more popular than others? Right? I mean, various people have looked at this. Kevin has a paper on it. Steve's going to talk about this right after lunch. I mentioned this at the meeting in Spain last summer, and Helfgott came up with what he told me was a proof, but he didn't write it down, and I don't remember I didn't understand what he said when he was saying it. But everyone's explaining this differently. But I'm not sure that anyone explains it completely, because you have these peaks, but it's kind of like a fractal. That is, it's like if you look between two peaks, it looks like a straight line, almost zero. But if you like focus on that, you'll get the same kind of spectral behavior between the peaks, right? So on ad infinitum. Okay. So the problem is, why are there these peaks? And for 4-element sets, they have to do with like the tetrahedral number differences. But let me skip all this. Let me just say one last thing about the sizes of some sets. Again, these are all ridiculous questions, right? So you can imagine, like there used to be this thing, like you take primes congruent to 1 mod 4 and congruent to 3 mod 4. And you have, say, up to X, how many are of each type? And it's sort of like a race. Like at one point, 1 mod 4 might be ahead, and then 3 mod 4 might be ahead, right? So you have like these prime number races. So you could also have like some set size races. So suppose you pick some big number h, like 100, and for every number little h from 1 to 100, let epsilon be -1, 0, or 1. So so the question is, can you construct, or do there exist, and then can you construct finite sets A and B such that for h going from 1 to 100, you can like demand in advance that the h-fold sum of A will be strictly less than the h-fold sum of B if epsilon h is -1, or equal if epsilon h equals 0, or 1 if epsilon h equals 1, right? That is, can you like fix the race, right? Okay. And the answer is yes. So this was solved independently by Paul Paranguet and Anne de Raton in France, and Noah Kravitz now at Oxford, I guess. Jacob Fox also got interested in this. And with Noah and with one of Jacob's graduate students, they did the following. Suppose instead of just having your, as you iterate these sum sets, H compared to A compared to B, 2A compared to 2B, 3A compared to 3B, you ask, you don't want to specify not that one is bigger or smaller or equal to the other, but you want to actually be able to specify the exact difference, right? So you pick an integer, positive, negative, or 0, delta sub h, for h from, let's say, from 1 to 100. And can you construct finite sets A and B such that for all h from 1 to 100, the difference in size between the h-fold sum set of A and the h-fold sum set of B is exactly this delta sub h? And that's a theorem of Fox, Kravitz, and Jang. Right? Very nice. So there are all sorts of problems about this. You don't have to look at the integers, and you can look at restricted sum sets. You can look at, instead of looking at just the simple subsets, you could look at, let's say, at linear forms determining the size. Okay, right. I'm not so bad. End of problem 1. Remember I said this is called 3 problems. So again, another, I don't understand why I thought of this as a question. So, a cofinite set's a set whose complement is finite. Co-infinite set's a set whose complement is infinite. You can have a sequence of sets that's strictly decreasing. Let's say these are, sets of integers, but they can be sets in any, let's say, additive abelian semigroup, if you like. So you take some family of sets A sub q in a semigroup, look at their intersection and call that A. So if A is the intersection of AQ, then the H-fold subset of A is contained in the H-fold subset of AQ. So the H-fold subset of A is contained in the intersection of the H-fold subset. And you can ask, are these ever equal? Or when are they equal? Or if they're, you can ask a question about that, right? So, so this is this is a result that says, if you actually take sequences of non-negative integers, they're always equal, right? For sequences of non-negative integers, right? I mean, this is a special case of a more general result, but they're always equal, right? For non-negative integers. On the other hand, if you look at integers, and all integers, allow negative guys in there, they're not necessarily always equal. So as the simplest example, suppose that the AQ sharp, this is all integers are in absolute value greater than or equal to Q. So the intersection of all those AQs sharps is the empty set, right? So the H-fold sum of the intersection is the empty set. On the other hand, for each of the individual AQs, the H-fold sum is always all the integers. So at this thing here at the bottom, on the left, HA sharp, the H-fold sum of the intersection is the empty set, but the intersection, but HAQ sharp is always Z, so the intersection is Z. So right, that's an example. And you can generalize this, of course, in lots of ways. Let's see, what does this say? If A is a basis, so if A is a basis of order H naught for Z, that means you have a set of integers, positive and negative and loud. And if the H-fold sum gives you all of the integers, then it's a basis of order H naught. So in that case, you get equality, right? Because, let's say, if A is a basis of order, H naught for Z, then yeah. So, all right, sorry. So if A is a basis of order H, the H-fold sum is Z, is all the integers. And if A is the intersection of the AQs are bigger, so the H-fold sum of AQ is all the integers. So you have to have equality there for H. But that's not necessarily the case if A is not a basis of order H naught. So, yeah, I'm sorry. So, yeah, I left out some slides here. But the first thing I said was if you have sets of non-negative integers, you always have that, and you look at a sequence of sets of non-negative integers and take the intersection, the H-fold sum of the intersection is the intersection of the H-fold sums. Notwithstanding the notion of trust, verify, not trust, or whatever. What? Trust but verify, yes. That's not true for all integers, right? If you look at the sets of all integers. It's also not true for sets of real numbers, even non-negative real numbers. So somewhere on the archive, I have a paper where this is all written down, but there's sets of real numbers where non-negative real numbers, where it's no longer the case that the intersection of the H-fold sum of the intersection is the intersection of the H-fold sum. And in fact, you can go, you can actually construct sets which are unions of intervals of real numbers where you no longer have this intersection property. But there has to be a problem, right? Here now I'm just like stating various results or facts. So this is what the sum set intersection problem is. You have an abelian semigroup S, a family can be a sequence of subsets of the semigroup. A is the intersection of the sets in the family. And we want to look at all integers h, where the h-fold sum of the intersection is the intersection of the h-fold sums. So by definition, 1 is in this set because A is the intersection of the AQs. So this script H of AQ is a sequence of sets, is some set of positive integers containing 1 and possibly only containing 1, right? But this is the set we want to understand, right? So the question is, what sets of positive integers are these sum-set intersection sets? And you can do it if you have a non-abelian semigroup and looking at multiplicative product sets instead of sum sets. So for example, if you have some infinite group, not necessarily abelian, and A is an infinite proper subgroup, then you can construct an asymptotically strictly decreasing sequence of subsets of the group where the only time the intersection property holds is with h equal 1, right? So actually, we've seen 2 examples of these sum-set intersection sets. So in this example, the sum-set intersection set just consists of 1 for sets of non-negative integers, all h. The sum-set intersection set is the set of all positive integers. So with a colleague, or friend, whatever, a guy in Brazil named Diego Marx, we actually have some constructions of other sum-set intersection sets. So for example, if you pick your favorite number greater than or equal to 3, there's a sum-set intersection set that consists of 1 together with all numbers greater than or equal to h naught, right? So that's something which is not everything and not just 1. And we have some other examples of this. So here are some problems. So this is the set of problems for this. If you take a set X of positive integers that contains 1, does there exist a decreasing sequence A sub q of sets of integers such that the sum-set intersection set is X, right? That is, can you get every set X of positive integers containing 1 as a sum-set intersection set for some sequence of integers? So for this, the Chudovskys set ChatGPT 5.5 Pro, the Tim Gower's favorite, on this. And ChatGPT came up with an answer of yes for finite sets, but only for finite sets. And it is a truly beautiful piece construction. I mean, you look at this and sometimes you look at it and you say, damn, I should have thought of that. But other times you look at it and you say, God damn it, that ChatGPT 5.5 Pro is really smart. I mean, it is it's not a trivial construction, and it's correct. So I'm sure it's correct, but I'm still trying to figure it out completely. Well, you guys are all here. If I were home, I would have done it by now. So for finite sets, every finite set of integers containing a 1 is one of these sum-set intersection sets for some sequence of sets of integers. You can ask the problem slightly differently. If you start with 2 sets, A and X, A is a set of integers, X is a set of positive integers containing 1, can you find some sequence of sets whose intersection is A and has X as a sum-set intersection set? Third problem is, for a given set A, you look at all sequences A sub q whose intersection is A and look at the sum-set intersection sets associated with A, right? Because you can have A as an intersection of sets in one way and A as an intersection of sets in a different way, and the sum-set intersection sets can be different, right? There's no reason why they have to be the same.
Do you have a set X that you know is impossible?
So For integers, for sets of integers, every finite set is possible, and infinite sets we don't know. But you can ask the problem more generally about semigroups. So given a set X, can you construct a semigroup S and a sequence of sets in the semigroup whose intersection has exactly the sum set intersection problem set X, okay? And Aristotle, smart guy, asked by Pietro Mattacone and Wouters von Dorn, proved the answer was yes. And this was the paper that they did and that I found on arXiv. And I was really impressed because I had proved a bunch of stuff about semigroups. I gave a talk here about Aristotle, and I kept referring to him, and someone said, how do you know it's a guy? So I asked the people at Harmonic what pronoun they use with respect to Aristotle, and they always call it. So Aristotle constructs a semigroup. So given a set X, it constructs a semigroup and a sequence of subsets of X, so that if A is the intersection of the sequence, then the h-fold sum of A equals the intersection of the h-fold sum of the HAQs, if and only if H is in this prescribed set X. Right? I mean, that's it's really pretty good, I thought. Okay, one last problem. I've got a few more minutes. Positivity and negativity. So there is a very classical problem in additive number theory. It says that a set of integers is an additive H basis for n if every integer from 0 to n is the sum of H elements of the set. So you look at the initial interval from 0 to n, and an H basis for n is a set A whose H-fold sum contains from 0 to n. Initially, everything in the subject was written in German, and the Abschnittspassen is segment basis. That's in general, we can say if you take any non-empty set A of integers, that n sub h flat of A, because there's something else I'll define, there's n sub h sharp, but n sub h flat of A is the largest integer n such that A is the basis of order h for n. That is, it's the largest integer n such that the interval from 0 to n is contained in HA. Now, I really, so this problem was introduced by a German mathematician named Rohrbach, Hans Rohrbach. And his problem was to determine for every positive integer k, the largest integer n such that n sub h of A is n, that is such that there's a set of size k, which is an H basis for n. And he published this in two papers, 1937 and 1938. So I was curious. So yesterday, Max was talking about the Vinogradov exponent sum for the prime exponential sum, whatever it's called, which was published in 1937, which was a difficult time in the Soviet Union. So, of course, 37 and 38 were also difficult times in Germany. And the second paper was published in the Jahresbericht Deutsche Mathematische Vereinigung, which was the official Nazi mathematics paper. And I looked up Rohrbach, and I was curious because I looked up his publications. He never published another paper in mathematics after this. But he became, with Hasse, the editor-in-chief of Krelle for about a quarter of a century. Right? And so what was his history? So he was a Nazi party member and a member of the SA. And during the war, he had two jobs, both mathematical. He was doing calculations for the German missile program. I guess, there's this famous song by Tom Lehrer about Werner von Braun. The famous line is, "When the rockets come up, who cares where they come down? That's not my department," says Werner von Braun. So Rohrbach was doing calculations on missile stuff, and he was also doing cryptography. So everyone knows how Turing broke the German naval code, Was that it? Rohrbach broke the American diplomatic code. And after the war, everyone meant the Russians and the Americans, went into Germany to try to grab the really smart guys and figure out what they had done. And so Rohrbach evidently wrote this long report on the mathematical methods he had used to break the American diplomatic code. But he stayed in Germany. It was kind of funny because according to the Wikipedia entry, he wasn't allowed to teach officially in the university, but he became like an adjunct. But in a short time, he was like the rector of the university also. And in the numerical work that he did in the German ballistics program, he worked with the logician Gensen, and who was also an SA member. But somehow Gensen pissed somebody off, and he was put into a camp near the end of the war. And but it wasn't clear whether the Germans put him in the camp or when the Russians came in, they put him in the camp, and he died of starvation in the camp in a couple of months. But Rohrbach never wrote another paper. It's really I found it very strange. There's some simple cases when we can compute when you only have one or two when you only have one or two elements. If you're looking at sets with three elements, n sub h3, that means you look at sets with three elements, non-negative integers, h-fold sums, and you want to know what's the largest interval from 0 to n that you can cover. And I thought this was in Rohrbach's paper, but I looked it up recently and it wasn't there. But it's as they say, it's well known. And I just, it's obviously easy to track it down if you look at enough papers. But this is the result. If you're looking at just h-fold sums of a set of three elements, the maximum n is given, it's roughly h squared over 4. And what it is exactly depends on whether h is even or h is odd. And for each of these two cases, you can write down exactly what are the extremal bases. Now, there's a sort of a combinatorial upper bound for how large n can be, which is just the binomial coefficient, which is roughly k to the h over h factorial. And they're very simple constructions. Like if you want to find a set with k elements and you're looking at twofold sums, you can take all the numbers from 0 up to k over 2, and then k over 2 multiples of k over 2. And that will give you roughly everything up to k squared over 4. And you can iterate that for h bigger than 2. So you get a lower bound of k to the h over h to the h. And what has been, I think this is still an open problem. I'm not 100% certain. It's just an old problem. If you look at n sub h of k over k to the h, whether that, so we have upper and lower bounds. We have the right order of magnitude for trivial reasons. And a lot of work has been done improving the upper and lower bounds. But no one's been able to say yes or no whether this limit exists, whether there's some asymptotic to this. Okay, so this is all well known. For whatever reason, I was thinking, suppose you allow negative numbers. Because in the Rohrbach problem, they're only looking at sets of non-negative integers. So you suppose you take a set of k integers and you allow it to contain a negative number. Can you do as well as just with the non-negative numbers? Can you equal it? Maybe you can do better, right? So I don't want to use negativity in a negative sense, but the question is, what happens if you allow negativity when you're looking at h bases for n? So I define this number m sub h of k. So you look at sets of k integers with at least one of them negative. And for those sets, you look at the largest interval from 0 to n that's covered by the h-fold sums. And so we want to understand what are these numbers. So there are three obvious questions. That is, if you're allowed negative numbers, can you get exactly what you get with non-negative numbers? Or do you do worse? Or do you do better? I know the answer. Because Aristotle told me. So Aristotle with Wouter van Doorn and Pietro Montecone and me, I'm only there because, I talk to them a lot. They talk to me, whatever. So if h is even and not 4, then with negative numbers, you can do exactly as well as just with non-negative numbers. In every other case, you cannot do as well as with non-negative numbers. And so then you want to see how smart is Aristotle really? Can you do, instead of just like this inequality, in the case when m sub h of 3 is smaller, what is it? So we know what n sub h is, right? That was this classical result, which is h squared over 4 plus something you can write down. But what is it exactly? So these are the values of this m sub h of 3 for all h. So if you're only allowed to take one sum, and you have to have a negative number, you better have 0 and 1. So 0, 1, any negative number will give you 0, 1. You can't do any better than that. For 3 elements, you can get 6. For 4 elements, for 3-fold sums, you can get 6. For 4-fold sums, you can get h. When h is even and not 4, this m sub h is this h squared plus 6h floor. That's exactly what you get with non-negative numbers. If h is at least 5 and congruent to 1, 3, 5, or 7 mod 12, there's this number. If h is 9 mod 12, there's that number. If h is 11 mod 12, we have it. If h is, the two other cases, if h is 59 mod 60, and it's really, it should have been written, if h is minus 1 mod 60 and not minus 1 mod 7, you have a number. And if h is minus 1 mod 60 and minus 1 mod 7, which is the same as minus 1 mod 419, you get this number. So these are the exact values for 3-element subsets. And what they are, I don't know if I wrote this down. One last thing. So what they are when you have sets with more than 3 elements, no one knows. I mean, Aristotle knows. You just have to ask it, and what do they call those things? Tokens, all right? Have enough tokens. Well, of course, Pietro Mattaconi works for harmonic. This is one of his one of the things he's actually paid to do. You might ask why, but I think I know why. So they have unlimited access to everything. Okay. Sorry. So this is the very last thing. So NH flat was the largest. So you have a set A, you look at the H-fold sums. The NH flat was the largest interval from 0 to n, which is contained in the sum set. NH sharp is the largest interval from U to U plus n, that is largest interval of length n anywhere, right? So you take your set A, you look at the H-fold sum, and you just look for the largest interval that you can find in that sum, right? And n sub h sharp of k is, if you look at all sets of k integers and their H-fold sums, it's the largest interval that ever occurs. So the largest interval is certainly at least as large as the interval from 0 to n that might occur. So this hn sharp is bigger than hn flat. And it's just an interesting question. As far as I know, no one's looked at it, but that doesn't mean no one's looked at it. But what this difference might be. And that is the end of the story. Question? If there are no questions, there's actually a few seconds of a YouTube video I want to show having to do with the ambitions of these companies that are trying to do this fancy math. So Kevin, you have to explain how to get rid of this. And so this should be on the machine already. Now, let me see if I can do this.
Okay, so you need to share.
Okay.
And do you want to stop recording or?
Yeah, stop recording.